Today I wanted to go through the firmware of the LED light project. I have developed it on an ESP32S3 dev kit board. This is typically what you do when you don't have your hardware yet and you don't have whatever stuff. But in reality, really I should have finished the hardware before starting, but I wanted to mix things up and so on and so forth. So before you even have your hardware, you usually develop on these dev kits, test your code out, put some LEDs or something in place of the actual thing, and theoretically it should all work out. But before we even start coding, I like to do a little functional flowchart diagram, similar to what we do with the hardware side, where we always create a flowchart to elicit what is the circuit going to do, what voltages do we need, what is the actual main functionality, how is everything connected. So we have this little state diagram, little diagram here, and this is the parts of our microcontroller, of our processor, what we are needing to incorporate into. So as you can see, we have GPIOs for the temp sensor and the motion sensor, and ADC for the status of our battery, with GPIO controlling the LEDs. The temp sensor, I think, should have gone down to the ADC, really, and this gives us an overview of what do we need. So we have an RTOS in there, we have the driver, so this is the driver we will write. We have a sleep function, so we will put this device to sleep. Coming down to the actual flowchart is what we need to know, and this theoretically should outline so someone should be able to see it and you can build off towards that. So we have our start, we're going to it should go into sleep, so this shuts down all the LEDs. Detected movement, no light, so yes, so this means the light is not on, the main light, but there is movement present. So we're going to wake up, read the pin of what the mode, LED mode, so we have separate modes to the RGB and the warm light LED, which one is going to incorporate first. We're going to read previous brightness settings, so the brightness setting should be always set whilst in the sleep mode and should boot up. If this doesn't work out, we can always decrease it down to the minimum brightness level or the max brightness. And then we're going to turn on the LEDs, and turn on the LEDs for 20 minutes. It's the timer we're going to set on, and then we're going to turn them back off again. I'm not too sure whether we need a real-time clock of some sort. I think we would need something of that sort, so something we need to keep in mind, maybe something it's worth putting into. Then we're going to turn off all the LEDs after this 20-minute timer. So, of course, again, nothing, and now that I'm speaking through this, we could put an interrupt in case, has the motion been detected again, interrupt, turn back on the LEDs. Again, this could work out perfectly, but it's some things we can change, and we can keep going into it. Put some notes here. Mode switch, the user can change the LED mode at any time, so this must ensure that we can switch between RGBW LEDs and warm white LEDs. They cannot be on at the same time due to current limiting abilities, and we do not want to fry our circuit, or at least damage any components and whatnot. So we need to include a feature to prevent this. We have a user has 4 brightness modes, 25, 50, 75, 100%, so they can adjust this. Notice I haven't put a 0 on there for the off state, and this is something we can incorporate later down the line. So in the actual code here, we have included as standard, you include your few header files for what you need, what you want to do. We have defined some GPIOs into what this is. So this is the brightness pin, the mode pin. So these are the 2 GPIOs we're going to use. We're just going to leave them to a button, and we have a brightness level of 1. So this is what we're initializing it as, and it's always good to comment and what because even just a week later you may not even know what you're writing, and this helps for readability and such. We are utilizing a semaphore, a mutex semaphore, and I'll go into a bit later of what that is and why we're doing it, but essentially it allows only something to write one at a time between a shared resource. So notice how I said before we needed a feature so we cannot have both on at the same time. This mutex, in my ideal head, should prevent this. Like we spoke about in previous videos, we can do this feature in software and hardware. It really just depends on what your conditions are. So we have some functions here. Always good to put everything in functions, as you can edit it out later. And if I scroll down into here to the actual main part, you can see this is the actual main part of the code. This is the thing that executes, but these are all the functions implemented. If you imagine that we had everything written down or wrote down between here, it would be quite messy and be quite hard to change everything out. But doing this like so, we have a case of small modularity in that we can easily change over what we need to change. It's the same as these brightness pins and whatever, we can easily change them out instead of addressing every single one. It's never a really good idea to put numbers or vague terms or arbitrary things, because you look at it and you go, oh, what's that? It's better to define it and say like this is a 25% brightness, or as a sort, for example here, warm white brightness 100. I could have just put the numbers in like 750, 1000, and I would have done the same, but it's always better to do this. So we're defining the config pin. This is kind of standard for what you do. You reset it, set direction, what pull-ups you want, what pull-downs you want. So this is a switch that will be active low, I suppose, and upon hitting low we can change the brightness config. Same again for the mode pin, exact same thing. And for the mode pin input, so only when our GPIO goes to low, and because we are utilizing a free RTOS in here, this is why we have the while loop. I'm not going to go too much detail into what free RTOS is. There's a lot of good information online, documentation, other people's videos that you can look into. So if GPIO get level equals 0, this is how we get our brightness pin, and we're going to increment the brightness by 1. So we have our brightness level, this is going to 2, and if you've seen later down in the function, we have done quite in some way or unique sense that we can increment the brightness here depending on the state of the brightness level. This is the exact same thing for the mode input. This is the same thing, we're doing it, then once it hits 3, because we increment, we're setting it back down to 1. Of course, there's always a million ways you can implement something. It's just the way I've decided to do it. So it's nothing really too complex here. We just have a bunch of if statements that we're cycling through, and then we're setting, oh, okay, if it equals 3, we're going to set it to 75% brightness, so on and so forth. The only key difference that some may have not found is this semaphore, and that we can release it. So once the mode has been selected, we have to think of it as a key and accessing 2 rooms. Without that key, so let's say RGB W1 is 1 room, RGB then LED warm light 2 is the 2nd room. The key is our semaphore. So once we have set mode select 2, we now have the key to access warm LED. Once we've done all our functions in warm LED, we should release the semaphore. So now we're giving it back. So say, okay, so this is already in mode LED. We have switched off everything on RGBW, so things cannot be on, they're not going to be on at the same time, and we're just going to enable the warm LEDs. So now okay, that's enabled, we can give back the key. And it's the same thing when we come back to the RGB, which is, I believe it's down below, or it's over here. Same thing for RGB. Once we take the key, we're going to turn off all the warm LEDs, going to set the RGBW, and then we're going to give back the key. So once we've set that, we've done what we need to do in this room, we're going to give it back. And we just put some delays in there so the watchdog doesn't kick, so we can kick the watchdog. And that's all that there is to it for this main part of the code. We're running 4 simultaneous tasks, and we set the priorities, and this is what we're going to do. You'll notice I have LED-driver.h, LED-driver.c. If we head into .h, it is just a header file for the LED drivers. And notice I haven't used any of these, so I could probably remove them, but these are all the declared functions and whatnot for my other functions in the .c file. So I'm using something called LEDC, and it's something you can find on the ESP32 website. And if we take a quick look at it, over here, the LED control LEDC, we can see a lot of information on how we're going to set up the functionality overview, how we can change the PWM signal over here, what we need to do for it, and there's lots of other APIs we can use, not just the 2 that I've used. In the code here we have the channel config and the timer config. So this is the timer clock which we are setting, and this is the channel config. So the channel config relates to the GPIO number you want to use and separate channels. So you can have up to 8 channels, I believe. But we can assign different GPIOs for these channels to the same channel. If we scroll a bit further down, this is the actual functions, and these are the 2 APIs we're using, set duty and update duty. So to change the brightness, we are just setting the duty to 250. So this is the actual bit number of it. So we have a 10-bit timer, I believe. We set it over here, or is it in channel? Might be in the timer config. So here we go. So we have a timer number of duty resolution 10-bit, and we're setting for 25 equals is for 250. And you may wonder, where do I get this fancy number? And if we open up our calculator, we will go to programmer, go to bin. So we have 10 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have a decimal value of 1023, quite a familiar number we see. And we divide this quarter, we get 250 roughly. So this is for a quarter duty cycle. Same for the 50 would be 500, 750, 75%, 750, and 100%, 100. Of course, it's not true, and when we look on the oscilloscope later, we can see this for what it's actually doing. So this is how we are updating it, and it's the same thing throughout all these other different functions. And this is how I am changing all the duty cycle of the devices. Notice I've put all the stop, so I'm setting them all to 0 to stop the RGB, stop the warm light, I'm setting it all to 0, and into config we are initializing all of them. There's so many more APIs on the website that you can have a look through and read through, but these are the only ones I needed to use. So do not limit yourself to them, because for example, if you had a fade application, there is an API for that. What's also a nice thing, if we go back to the website, they do have an example here. So in this example, we can look through and see how they've done it and and you know, they've given some waveforms nicely and for what you expect when you're doing your own type of thing. So do have a read through if you need to. So I'm going to elicit the functionality of the LED and I'll be right back. So here we can see the waveform that's being generated. So we are on third, so 75%, and if we press the button again, you can see we're near 100%, and we can see a slight dip over here because we're not running at exactly, I think it's 1023 10-bit, and we can check this if we get the calculator out and we start putting 1 2 3 4 5 6 7 8 9 10 1023. So if this was 1023, we get it fully straight, and we press it again, we're going back down to 1, so 250 we have it set, and this is evident in our waveform. So this is how we can adjust the brightness, and it's because we're only having the on time for a set period, but we can see in the camera and to our eye that we don't see this on and off. It's too fast for us to see anyway. So this is also one method that's employed in you know, for PWM in generally, we can use this to adjust the speed of a motor or dimming light application. It's also good for power consumption, for saving. So obviously at 25, when it's not on all the time, not continuous, we're saving a lot more power. We can just adjust this again and we can see the waveform change with it. So I had to do 2 separate recordings for this, but so one will illustrate the PWM changing, and then that was previously when I previously recorded this before I updated everything. So this will illustrate the mode and you can visually see what is actually going on. So we have our mode pin, I believe, or the brightness pin, mode pin. We're going to change in between. So right now it's in RGBW. My buttons are a bit weak here, so that's turned off. That's went back to red, so that is the lower setting. So you can see it's getting brighter with a button press. So there. So this should be at 100, I think. It should go back down to 25. So you see there's a bit of a delay in there. That's because we'll have added in before it changes back, but we can remove that. And this is why it's always good to prototype your firmware. You can actually see in real time what is actually going on. So you press this, and then we've changed it back to warm light. So this one's turned off, this has gone up to here. If we try and increase this, so this looks like to be on 75, well, and you can see the brightness has followed from the yellow to the red. So we're quite happy with this functionality. We're quite happy with it. It's just a small delay we have to adjust to account for it, and we can want it as an instant type of thing. As you can imagine, with a user might thinking, oh, there's something wrong, and they keep pressing it and it might not ever come live, and then it's a poor user experience, really. It's just these small things that we need to make changes to. Yes, but back here now, and before I end off and things, I wanted to speak a bit more onto why you might want to separate these things out. You see a lot of these with bigger projects. You probably have more header files, have more other C files and whatnot. But the thing is with this is that it helps to separate out, and you may have a function for each. So perhaps later down the line, I may have a separate driver file, I don't know, for a specific functionality. I can't really think of something on the spot here, but let's say if you had a GPS application, you would have a driver file and a header file for that GPS. Then you had accelerometer, you would have something for that. It's noticed when you go into other, using different components and such, there's always a header file, source file associated with that. And it's something to easily spread out. And of course, if you really want to, you can put everything in the main source code, but I don't recommend it. It's too messy, it's too clunky. So that's all I want to talk about. We have later on to finish off the hardware design of this project and actually get it ordered through so we can actually play with the physical part of it.